Welcome, everyone. What we're going to be talking about today is the immune-humanized platforms that are offered by the Jackson Laboratory. So before I get started, let me talk a little bit about the Jackson Laboratory. And first is our mission. Our mission is to discover precise genomic solutions for disease and empower the global biomedical community in the shared quest to improve human health. And we do that in multiple ways. Most of you are very well aware that we have more than 12,000 strains in our collection, and this is a wonderful resource for obtaining and using mouse models that are integral to your research. But what many people don't know is we also offer a wide range of services based on the mouse platforms. They include creating new strains, breeding up new strains, understand their phenotypes, their natural history of disease, and very importantly, into rolling them into efficacy studies, doing contract research for a wide range of organizations, including academics, biotechs, big pharma, et cetera. And we are a global institution. We have multiple sites in the United States. We also have distribution points in China, and we also have distribution and provide services in Japan. So let's begin by really taking a look at what we mean by a humanized mouse, because there are multiple ways in which this term is used in the literature. One way is the DNA or genetic modification of the immunodeficient mouse itself, or even immunosufficient mice to express human targets. But also in the context of immunodeficient mice, genetic modifications to introduce different growth factors for different cell populations. But then there's the straight up adoptive transfer or the transplantation of either peripheral blood mononuclear cells or human hematopoietic stem cells to reconstitute the immune system with human cells in these immunodeficient mouse platforms. And then, of course, the most advanced humanized platforms are both genetically modified to express human factors that support the growth, differentiation, and function of engrafted human cells. So most of the models that I'm going to be talking about today are a combination of genetic modification and the engraftment of these human cell populations. Now, as I pointed out, there's two different sources of hematopoietic cells that are commonly used in engraftment: PBMCs or the human hematopoietic stem cells. And the types of cells and the maturity of those cells that reside in the peripheral blood and other tissues of these mice are going to be different depending on the source of cells that you use. There are going to be multiple cell populations that are engrafted following PBMCs. Not shown here, they also include natural killer cells and myeloid cells, but at much lower frequencies. With the hematopoietic stem cells that are engrafted, you get true multi-lineage engraftment, where basically all cells of the hematopoietic compartment are represented in these mice. However, the caveat to that is there are a number of innate immune populations specifically that are present but are available at really low frequency. And it's these populations and several others that really need human-specific growth factors to support their growth, differentiation, and maturation. So let's start out with chapter 1, really focusing on the PBMC engrafted models. And there's going to be two of them that I'm going to be discussing today, the NSG and the NSG MHC class 1, class 2 double knockout. And let's talk about what they are and what's different about them. So the first thing I want to say, though, is that the leukopaks are a wonderful source of cells. And what's really wonderful about them is you literally get hundreds of millions of cells that can be stored away, and you can pull cells from that leukopak, put them in mice, and do this and create large cohorts of mice, and you can build upon your studies. In other words, you can go back and repeat studies and build on doing sequential sets of experience, doing combinatorial therapies and things like that. Now, the most classic model that's being used for this today is the regular NSG mice, the NOD-SCID gamma mouse. Human PBMCs are injected, and of course, they're going to lead to xenogenic graft versus host disease. That's because the human T cells become activated against mouse class 1 and class 2. And we take advantage of this as a platform for testing immunosuppressive therapies primarily. These immunosuppressive therapies can be applicable to graft versus host disease itself following allogeneic bone marrow transplantation, suppression of the immune system following organ transplantation, or the suppression of the immune system in the context of autoimmune disease. However, some people want to look at activation of the immune system, and this is relevant to the field of immuno-oncology. And due to these complications with xenogenic graft versus host disease, Lenny Schultz and his colleagues working at the Jackson Laboratory created this new mouse model, which is knocked out for both mouse class 1 and class 2. The elimination of class 1 and class 2 allows for the study of human T cell function with highly diminished xenogenic graft versus host disease. It doesn't eliminate it completely, but it gives you a window of opportunity that now you can co-engraft human tumors and then treat these mice with different immunotherapeutic approaches that allow you to study that mechanism of action without that inflammatory complication of xenogenic graft versus host disease. So let's dive in a little bit more to what's expected following the engraftment of these PBMCs, because there's a lot of different factors that are going to influence the rate, the severity, the progression of engraftment, the development of graft versus host disease, et cetera. One of them is irradiation. And when I say radiation, I mean sublethal irradiation, because with PBMCs, you are not going to be able to rescue the mouse survival using lethal irradiation like you can do with hematopoietic stem cell engraftment. There's just certain populations like the erythroid compartment that is not going to rescue the animal. So in graphic A over here on the left, this is if you just irradiate with sublethal irradiation, the mice survive long-term just fine. You can engraft these mice, in this example, 20 million human cells. They will develop, this is in the NSG recipient, just to make sure that is clear to everybody. This is the kind of mean survival time of about 35, 40 days that you'll get the absence of using sublethal irradiation, and you will accelerate engraftment and accelerate the development of graft versus host disease using the same dosage of cells, but including sublethal irradiation. And the loss of body weight very closely tracks with the development of graft versus host disease. So you can use that as a proxy to understand the health of the animal overall. So with high dose of cells and irradiation, they're going to develop GvHD very quickly. You leave out irradiation, it's going to take more time for engraftment, and then they'll slowly become ill over time. And then they'll drop a little bit of weight with radiation alone, but then they'll bounce back over time. Now, what's also really important to note is that cell dose is going to make a big difference too. And so the more cells that you put in, the more rapidly they're going to develop graft versus host disease, and the shorter their mean survival time is going to be. Now, the other aspect of this, which I'll come back to multiple times within this presentation, is each leukopak is also going to have a different influence on the rate and kinetics of this whole thing. And every leukopak needs to be titrated to really understand what these kinetics are going to be. So the beautiful thing about this platform is there are multiple ways in which you can obtain readouts for your interventions for immunosuppression. And you can dive into the different tissues. You can look for immune infiltration. The brown staining is the human cells infiltrating the spleen, the liver, the lung, the duodenum, the skin, etc. You could look at hematocrit because these mice will develop anemia over time, a loss of platelets, etc. You can look at release of pro-inflammatory markers. You can harvest the cells from the peripheral blood and the spleen, and you can look at activation markers by flow cytometry. And so there's a wide range of methodologies for looking at mechanism of action and success in your immunosuppressive treatments. And again, I'm going to stress this again. The graft versus host disease develops irrespective of the allogeneic human donor, but the rate and the severity of disease progression are going to be donor dependent. So it's not only the genetics of the human donor, but it's also likely the immune experience of that human donor and the physiological state, pro-inflammatory state of that donor upon the time at which it was that person was donating those cells. So diving in a little bit deeper here, looking at a bit of a time course, this is in the context of, again, the NSG mouse, irradiated, injected with 20 million PBMCs. We're looking at dark green day 5, lighter green hatched is day 10, and we're looking at 4 different donors, 309, 213, 345, and 364. What you can see from here is that the expansion of the cell is very rapid in this context, very much jumps up in total CD45 from 5 to 10 days for all of these donors. And within that CD45 total human population, it's going to be dominated by CD3 T cells, and you can further dive into this and split this into CD4s, CD8s, and you can use flow markers to look at naive, central memory, effector memory, and all those different populations. There will be CD19 and CD20 positive B cells that will be engrafted. They tend to decline over time. There are different quantities of CD14 and CD33 myeloid cells. They also tend to decline from peripheral blood over time, and natural killer cell population. So there are a wide range of cells that are engrafted, and each donor, the profile of the cells that engraft are very different. What is different from donor to donor, and we'll dive into this more, and I'll show you much more details if you join us again in April, talking about the responses from these different PBMCs. So the engraftment is often very, very similar, but the rate of engraftment can differ, and the immune responses from those cells can differ over time. All right, so now let's talk about the NSG class 1, class 2 double knockout. This is a wonderfully divergent platform that really allows you to do a lot of different things. You can co-engraft the PBMCs, and you can use labeled liquid tumors, B-cell and T-cell lymphomas. You can subcutaneously engraft tumors, or you could orthotopically graft mammary tumors in the mammary fat pad. And based on what you expect from your study design, your drug that you're going to be delivering, the mode of action, whether that's bispecifics, monoclonal antibody therapies, CAR T therapies, will depend on whether you put the tumors on first or then you put in the PBMCs. In most cases, when we do in vivo efficacy studies, most of the time we're putting tumors on board first. In that context, you may or may not want to use a radiation. We use a radiation for liquid tumors. Obviously, you don't want to expose your solid tumors to a radiation, but it's a very, very versatile platform that can co-engraft both. In the exact methodology and the timing at which you engraft these populations really depends on what you're working with, what tumor volume, what tumor burden you want to be looking at, whether it's low versus high, doing prophylactic versus therapeutic studies. All those things come into play. But the advantage here is that in the lack of the class 1 and class 2, and using a short working window, you can really have a time period which is devoid of the acute graft versus host disease responses. So what we're looking at in this graphic here is if the mouse is just a class 2 knockout, shown here in green, which is important for the activation of CD4 T cells, there's only a marginal increase in the survival time of these mice. If you knock out class 1, which is important for activation of the primary effector cells, CD4s certainly have effector cells as well and can be activated for killing, but CD8s are the primary effector cells. So if you knock out class 1, you have the biggest jump in the expansion of the survival of the mice. However, if you knock out both class 1 and class 2, this gives you the greatest window of opportunity with which to work with these. And this, just to be clear, this particular setup is using 10 million human PBMCs injected intravenously into non-irradiated recipients. So if you did the exact same work but included irradiation, all of these survival curves, the mean survival time would be shortened and everything would be shifted to the left. Okay. The other thing I'll point out quickly, this paper, I believe, points it out quite nicely too, is that there is a difference in these kinetics, whether you're doing IV administration or intraperitoneal introduction of these cells. So it takes a longer time for these immune cells to move from the peritoneum and into the bloodstream if you use IP. So this is just kind of a reiteration of this difference between the double knockout and the regular NSG in terms of survival. But I included this here because I also wanted to point out the kinetics of engraftment over time, so you get a feel for that. And also what you will recognize is that because of the delayed or slowed activation of these cells in the double knockout, the overall level of engraftment is going to be a little bit lower as well. So the percentage of the cells in the peripheral blood of those recipients is going to be lower. So it's going to be lower in the absence of irradiation, and it's going to be lower in the context or lacking of class 1 and class 2. But it's going to allow you to do things like bispecific T-cell engager work and CAR T and those other kinds of things. But what's important to point out is making sure that everyone is clear that even in the context of not having the mouse expressing class 1 and class 2, if you look at these T-cell subsets 4 weeks post-engraftment, they are looking very similar in terms of their immune phenotypes when you're comparing the NSG, just the class 2 knockout, the class 1 knockout, or the double knockout. And this is just a snapshot at 4 weeks, but we've also done progressive studies where we've looked across time at the development of these cells. And what you'll see is very early on after engraftment, you're going to have a high frequency of naive cells and lower frequency of central and effector memory cells, et cetera. The longer those mice are exposed to the tissues in the animal in vivo, naive cells will go away and you'll develop more central and effector memory cells over time. And you can track this time course and you can use that as a tool for looking at your immunosuppression. So this is the CD4 subsets, these are the CD8 subsets. And one thing that was noticed in this particular study is there is a slight increase in naives and a slight decrease in these effector and effector memory populations in the CD8 subsets post-engraftment in this context. But remember, these cells will be activated against other antigenic stimuli, even in the context of class 1, class 2 double knockout. So what happens in the context of irradiation? Well, you're just going to be speeding up the kinetics of all this. When we're looking at the class 1, class 2 double knockout in green, the NSG in blue, I'm just looking at 5 days post-engraftment in the irradiation setting. You get a really similar distribution of the cell populations between both models and across these different cell types as we saw previously. The major difference is that the NSG mice, those cells are going to be activated and they're going to be damaging tissues very quickly. The mice are going to be losing body weight, whereas in the class 1, class 2 double knockout, they don't lose body weight and they maintain longer term survival. Going back to this concept of donor to donor differences though, a different donor with the same dose of cells may have different kinetics, and that different donor, you may start to see mice losing weight and seeing a greater loss of survival, or yet a different donor that would have longer term survival than this particular mouse that lost like 1 out of 4 or 5 here. So each donor, even in both host contexts, is going to have different kinetics, and that needs to be understood as you're working with those cells. However, when you repeat the engraftment with those cells in a new cohort, you should expect to see the same results. All right, so again, in the context of irradiation, just bringing home this point again, looking from day 5 to day 2 in these different populations in the context of, and here, this is 20 million cells, IV injected radiated recipients. You're just going to see overall engraftment differences, but they are going to expand from day 5 to day 10, and you're going to get these different cell populations that are pretty similar between the 2 different platforms. So going back to, so which one is the better one for you in terms of the NSG or the double knockout? General theme is that the NSG is great for testing immune suppression. The double knockout is really better for testing immune activation and doing things like immuno-oncology and co-engrafting in tumors and things like that. Technically, you can do that in the NSG, but you have a really, really short window of opportunity in which you can work with those mice. If they're radiated, you've only got 10 to 14 days. You get out to like 30 days in the double knockout. If you really have a slow-growing tumor, you might be able to get it in with this 15 to 20 mean survival time, probably not with the NSG, and you're going to want to be thinking about maybe a solid slow-growing tumor. You really need to have a lot more time to work. You want long-term progression of your studies. Maybe you want to go to node irradiation in the double knockout. So again, these kinetics and the overall levels of engraftment that you're seeing here in this chart will again be influenced by the specific leukopak that you're working with, and there will be some differences from one cell population to the next, so be aware of that. Okay, now let's go over and let's start discussing the hematopoietic stem cell engrafted platforms. All right, so there's a number of different sources that have been reported in the literature for where you can get your human hematopoietic stem cells. The most commonly used is the umbilical cord blood derived. Those are readily available. There's a number of commercial resources. Many hospitals provide the opportunity to obtain these cells. And this is the cell population that the Jackson Laboratory is using in what we call the JAX production method, because we're engrafting these mice, setting them up on the shelf, verifying their engraftment, and you could literally buy cohorts of engrafted mice right off the shelf that are verified for engraftment. But you can use peripheral blood, mobilized hematopoietic stem cells, bone marrow aspirates, and isolate those cells, and fetal liver. The advantage of the fetal liver is that you can engraft a piece of the fetal liver and a piece of the fetal thymus under the kidney capsule, and then isolate those hematopoietic stem cells from that fetal liver, co-inject those, and you've got human thymic epithelial in which to train those human T cells that emerge from the bone marrow compartment of those mice. Most of the literature that you're probably familiar with are using neonatal mice, either using hepatic or intracardial injection of cells. The challenge with this model is that there's a lot of animal husbandry, and the number of mice in a cohort can be difficult to set up. It's a very challenging, technically difficult thing, and not something that can be readily done at scale. People do interfemoral injection if they're doing really specific hematopoietic stem cell populations that they don't want to be influenced by the IV administration and waiting for engraftment and migration to the bone marrow. And things like that. For production purposes, the Jackson Laboratory has gone to 3 to 4 week old animals with IV administration. This allows us to use more animals and create larger cohorts. It's a younger animal, so there's more thymic tissue available for getting good T cell education and training. For example, you can engraft through this methodology in 6 to 8 to 10 week old mice, but the cells that develop and the T cell development is not quite as good, and there's other cell populations that don't seem to do quite as well. So there is an advantage to using younger animals. So these are the different mice that we use. We don't use the double knockout for hematopoietic stem cell engraftment. We do use the NSG, the IL-15, the SGM3. And there's 2 new mouse models that we're going to be putting into service this year. This is an F1 hybrid between the SGM3 and the IL-15. And I'll go, in the next couple slides, I'll give some more details about what these are and what the advantages are for them. And then there's a new mouse model here that we call the FLT3 transgenic mouse. And we'll now go into what the differences are between these host platforms. And then we'll spend the remainder of the talk looking at the hematopoietic differences following hematopoietic stem cell transplantation in these different models. So the NSG is kind of the gold standard, and we compare everything to the NSG because this was the first mouse demonstrating really good hematopoietic stem cell multilineage engraftment. They have very good T cell education and function, but because of the lack of certain human growth factors, they have limited human NK and myeloid lineage development. So based on that, this mouse was created and donated to the Jackson Laboratory. This is an NSG mouse called the SGM3 because it's expressing stem cell factor, GM-CSF, and IL-3. And these mice promote improved AML engraftment, but also improves the myeloid cell development after hematopoietic stem cell transplantation. So it's expressing human stem cell factor to help the most primitive hematopoietic stem cell compartment. GM-CSF and IL-3 help produce and expand these multipotent progenitors, and this leads to improved myeloid and conventional dendritic cell development. What these mice happen to lack still is the human NK cell compartment. So if you look in these 2 mice, you can find functionally mature natural killer cells, but their frequency and numbers are low, and there's a fairly large population of underdeveloped cells. So in comes the NSG IL-15 mouse, which is expressing physiological levels of human IL-15, and it really enhances the development of these human natural killer cell populations. So because of the lack of a more complete innate immune system, we have bred together the SGM3 transgenic with the IL-15 transgenic, and we call this the NSG SGM3 IL-15. And this supports both worlds, as shown in blue here, the myeloid development, the conventional DCs, and the natural killer cells. However, some other cell populations are pretty low, like plasmacytoid dendritic cells, and we'd really like to see even more conventional dendritic cells. And so what was created here was this new mouse called the human FLT3 ligand. Human FLT3 ligand is very important for early hematopoiesis and also helps to accentuate some of these later lineage populations. And I'll go into a little bit more detail. So there's a really good, more improved overall multilineage reconstitution in this animal, as we'll see in a moment. And again, this mouse expresses physiological levels of human FLT3 ligand. Okay, so let's talk a little bit more about what's happening post-engraftment of these cells. The hematopoietic stem cells will naturally home to their niches in the bone marrow compartment. They will begin dividing, differentiating, and expanding mature cells out into the periphery. After a few weeks, you can isolate the thymus from these mice, find the double positive immature T cells that get selected on mouse thymus to become CD4 and CD8 single positive cells. You can track these cells, as I said earlier, over time. You can use flow cytometry markers to track the different distributions of naive cells, central memory, effector memory cells, TEMRAs, both within the CD4 and CD8 compartments in the spleen, the peripheral blood, mesenteric lymph nodes, etc., and demonstrate that these populations exist and are expanding over time. We know that they're being selected on the mouse thymic epithelia because of studies like this, where we take an immunodeficient mouse that has not been hematopoietically engrafted and put black 6 skin on it. Black 6 has a H2B immune haplotype, whereas the NSG or non-genetic background is an H2G7 haplotype. Therefore, they're mismatched, but in the context of no immune function in the NSG, lacking B cells, T cells, natural killer cells, etc., they are immunodeficient enough, they will allow the engraftment of these black 6 skin graft onto the flank of these NSG mice. However, if you transplant these mice with human hematopoietic stem cells, those T cells get trained on the mouse thymus and they recognize that black skin is foreign and they reject those skin explants very, very quickly. And the nice control here is if you take human NSG skin and put it on a humanized NSG recipient, they accept and engraft long-term just fine. The other important thing to demonstrate just a little bit here, and as I said, we'll go into more of this in April 4th in that particular webinar about immune modulation, is that you can do things like treat these mice with monoclonal antibodies that deplete T cells and see changes in immune function. And in this case, changes in rejection of those skin fragments. So in blue, that's a single dose of T cell depleter, 5 doses in green, or 7 doses in purple. And you can see that you knock down those T cells and you get long-term survival. The corollary to that is you can activate these cells with anti-CTLA-4 monoclonal antibody, ipilimumab. You can activate those T cells and you can accelerate rejection. So this is a quick demonstration that you can actively manipulate the immune function in vivo in these mouse models. Just a little bit about the development of the myeloid cells. This is still in the NSG CD34 engrafted model. You could see that there are neutrophils, monocytes, different dendritic cell populations, mast cells, basophils, et cetera. But it's important to recognize that the frequency of these cells is extremely low. For example, if you look at the neutrophil frequency, it's very, very low. It's down around 1, 2, 3, 4, 5%, something like that. With human peripheral blood, you're really going to be looking at something like 60, 70%. So that's the difference, and that's why we're creating these different transgenic models to boost those immune cell populations. Nevertheless, you could treat these mice with lipopolysaccharides and get immune responses. You could isolate these myeloid cells, put them in culture, you can get phagocytosis. So these are functional immune cells. It's just the frequency is low. And as you might expect, if you compare the lymphoid subsets to the myeloid subsets in the peripheral blood, you're going to be very lymphoid skewed. We do need these transgenes to upregulate the frequency of these myeloid subsets, and we'll see that you can accomplish that in the SGM3 model in just a moment. Same for the spleen, it's very lymphoid skewed. And then as you might expect, there's greater representation of the myeloid compartment in the bone marrow. So this is a nice paper comparing the NSG to the NSG SGM3. As a quick reminder, this is expressing transgenically the stem cell factor, GM-CSF, and interleukin-3. And if you look at the spleen, the liver, and the bone marrow, and you're looking at the immune populations in these different organs, you can see that in orange with the SGM3, you have increased frequency of cells with these myeloid markers. Interestingly, you see an increase of cells with the marker CD117, which are mast cells. Mast cells, CD117, they respond to human stem cell factor. That's why these mice are also a good mast cell marker, and I'll show you some more data for that in a minute. But you could see that overall, there's a lot more myeloid reconstitution and an increase of bone marrow-derived dendritic cells in the SGM3 as well. Taking another closer look at this, when you have the expression of these human growth factors, you're going to accelerate the engraftment. This makes sense because you're making human stem cell factors, so you're going to push these cells out of the bone marrow and into the peripheral blood much faster. So this is just comparing percent human CD45 between these two models over time. And over here, I'm breaking it down into the NSG mouse versus the SGM3, because the biggest difference between the two is the development of regulatory T cells in the myeloid cell compartment. There's much more development of a high frequency of regulatory T cells in the SGM3. And the engraftment kinetics change over time. So really are between, 10 and 15 weeks, you're going to have the maximum number of these regulatory T cells. It's often shown that the myeloid cells emerge from the bone marrow compartment first. As the T cells emerge and go out into the periphery, the percentage of those myeloid cells is decline as these T cell populations increase. And so it really takes about 12 weeks before everything really kind of settles down to a steady state and reaches equilibrium long term. These regulatory T cells are functional. They are present in the blood, the liver, the spleen, and the bone marrow. You could pull them out of the spleen and put them in mixed lymphocyte cultures where T cells have been activated with CD3 and CD28. Their membranes have been labeled with CFSC, a fluorescent marker, such that when they are activated, they divide and they lose fluorescence. But if you add in CD4, CD25 positive regulatory T cells, you keep those cells, you immunosuppress those cells and prevent them from dividing so they maintain the fluorescence in their membrane. Again, this is going back to the mast cell stories. If you look for a co-expression of the markers CD117 and FC receptor 1 alpha, FC epsilon receptor 1 alpha, you can find those cells in the spleen, the lung, and in peritoneal lavage. And people are doing anaphylaxis work with these mice. So as a quick summary, when compared to NSG, human CD34 cord blood HSC and grafted SGM3 mice have increased T cells, Tregs, CD33 and CD14 positive myeloid populations. So they do have improved myeloid cell development. And data I don't have time to show you today, but I will talk about this in a few weeks, is you can go and co-engraft these mice with human tumors and do a number of immuno-oncology, preclinical testing type of work with this platform. Now let's shift over to the NSG IL-15 mouse. On this graph at the left side of your screen, we're just looking at percent human CD45 in the peripheral blood of the human cells over time. And we're also looking over here on this side, the cells per microliter. So we could see that the cells per microliter also increase on both models in the total human population over time. Here we're looking at the T cell population comparing the two different strains. Blue circles is the NSG and the red squares is the IL-15 transgenic. The CD3 population is pretty similar as it develops over time. And again, you've got to wait till at least 12 to 14 weeks to see reasonable populations of T cells because they've got to go through thymic selection, et cetera. The CD4 to CD8 ratios is a little bit skewed at about 10 weeks, but it evens out at 12 and 14 weeks between the two models. A little bit lower frequency of human CD20 positive B cells within the IL-15 transgenic mouse. But the percentage of myeloid cells that develop over time is pretty similar between the models. Again, the frequency or percentage of these cells drops over time because all these other cell populations are increasing. So what about the NK cells? So the NK cells emerge very, very quickly in terms of frequency, and their frequency drops down because some of these other cell populations are expanding. But by the time you get out to 12 to 14 weeks, if you compare them to the frequency of NK cells in human peripheral blood, they're very, very similar, and they're higher than what you would see in the regular NSG mouse. This is answering the question, well, what about cell numbers in terms of cells per microliter in the peripheral blood? The cells per microliter are actually pretty stable over the course of engraftment. And this is just a look at, in more detail, the cell surface phenotypes by flow cytometry of these cells in the peripheral blood. Typically, the mature NK cells are CD56 intermediate CD16 positive, or this population that resides here. So in the NSG, they're at relatively low frequency, and they're at much higher frequency and higher cell numbers in the human IL-15 mouse. And of course, if you interrogate those NK cells further, you see a wide range of cell surface markers that you would expect to see on natural killer cells. If you look at granzyme B expression, you could see that in the NSG IL-15 mice, they mimic what you would see in cells isolated from peripheral blood. And in NSG, there is a subpopulation that haven't fully matured and are granzyme B low. If you take these cells from the IL-15 mouse and give them targets in an in vitro killing assay, you could see that their killing response very much mimics what you would see in the human peripheral blood cells. So the primary difference between the NSG and the the IL-15 transgenic and the regular NSG is just the expansion and the maturation and function of these natural killer cell populations. So if you're very interested in natural killer responses, ADCC responses, in the context of immuno-oncology or other disease settings, this is the platform for you. So, of course, we want to increase the functionality in the cells represented across all of innate immune function. So we set out to see if we could do that by simply crossing the SGM3 to the IL-15, creating an F1 hybrid between these two platforms. And what the data I'm going to show you next is that we use 3 different donors, and we're comparing the regular SGM3 to the SGM3 IL-15. So what we've got is on the top row is the SGM3 mice. The bottom row is going to be the F1 hybrid SGM3 IL-15. And there's 2 different donors, and you can look at the donors in columns, if you see here. And we're looking at T cells, maybe just pan T cell marker like CD3, CD19 for B cells, CD33 for myeloid cells, and CD56 for the natural killer cells. So I'll draw your eye first to the blue triangle lines, and you can see that in the NSG across these 3 donors, the NK cell populations is pretty low, but the NK cell population is very much increased across all of these donors when you look at the F1 hybrid. The other cell populations, when we're comparing these 2 different host populations, T, B, and myeloids, is very much unchanged across these 2 platforms. And it's really the inclusion of IL-15 that leads to the increase of the natural killer cells in these recipients. This is another way of looking at it. This time, this is really looking at the F1 hybrid in black and the SGM3 control in purple diamonds. And you can see that the percentage of these cells, percentage of NK cells as a percentage of human CD45 is increased across the board, across all 3 donors in the F1 hybrid. But this is also true in terms of cell numbers. So the cells per microliter is also increased across all 3 of these donors. Another thing that's interesting here, we're doing some more deep phenotyping across all of our platforms. And this is a sampling of that data. Here I'm comparing across the top row, the 4 different strains. And the top row is the frequency and the bottom row is the cell number. And what I'm looking at here is the mature NK cells that are 16 positive, 56 positive, and granzine positive in the blood. And what's interesting, if we compare the IL-15 to the F1 hybrid, the actual NK cell frequency and numbers are lower compared to the straight up IL-15. And the reason for that is that this is an F1 hybrid, so the IL-15 is hemizygous in this context. And so we think that our current hypothesis is that's the explanation, is that the overall expression of IL-15 in this mouse is lower, therefore the frequency and numbers of those cells is a little bit lower. What's interesting, though, is that in the SGM3, the frequency of many of those cell populations that support those myeloid populations remains just as high in the F1 hybrid as in the other mouse, and I'll show you that in a minute. So this is the spleen shows the same change in phenotypes. In other words, the F1 hybrid has lower frequency and numbers. So this is similar across peripheral blood and spleen. Coming back to the regulatory T cells, within the SGM3 versus the F1 hybrid, the regulatory T cells have the same frequency and cell numbers in the blood of these mice. So in that context, for reasons that aren't completely teased out yet, the SGM3 alleles still support the same frequency of the regulatory T cells. So a quick summary of this model. When compared to NSG, this F1 hybrid has higher T cells, more Tregs, more myeloid cells, and an accentuation of mature NK cell population. So they have an overall improved, enhanced innate immunity. And again, wonderful tool for co-engrafting human tumors and using this platform for immuno-oncology preclinical testing. So the last model in our collection that we're going to go over today is a new mouse model that we have, which is called the NSG FLT3 knockout human FLT3 ligand transgenic. So there was a lot of data to support that human FLT3 ligand would support hematopoiesis. And so the first mouse model that was created was just a transgenic expressing human FLT3 ligand. So Dr. Mike Brem at UMass Med was one of our long-term collaborators working in conjunction with Dr. Lenny Schultz. They created this mouse first, and they compared the stem cell engraftment between the NSG and this mouse. And they were disappointed to learn that this just introducing human FLT ligand by itself didn't lead to great results. There was a disappointing lower level of overall human engraftment. And the overall reason for this is because both mouse and human cells can bind, recognize, and utilize human FLT3 ligand. So in stage 2 in the creation of this mouse, they had to knock out the mouse FLT3 receptor to get good levels of engraftment in this doubly genetically modified mouse to get good levels of overall CD45 engraftment comparable to the NSG. So sometimes you have to do multiple genetic modifications to get a strong impact of these human growth factors that you're introducing to these mice. So these are the T cells. There's a slight increase of the T cell population at later time points in the FLT3 mouse. The B cell compartment is actually lower compared to what you would find in the regular NSG. Both the CD33 positive myeloid and the CD14 positive monocyte populations are increased in this mouse when compared to the regular NSG. The conventional dendritic cell population is expanded in this mice. And this is an interesting set of data points. When this work was done, these mice were engrafted at about 6 weeks of age. So these older mice seem to show a decline in these plasmacytoid dendritic cell populations. Later on, there was additional studies, and this time going back to 3 to 4 week old recipients. And when you introduce the hematopoietic stem cells in these younger FLT3 recipients, you have a maintenance and increased numbers and frequency of these plasmacytoid cells out at 15 weeks. So you can increase this population of these plasmacytoid cells at later time points simply by backing up the time point and the age of the recipient in which you engraft them. So there's another interesting story in these mice is if you look at CD56 positive, CD16 negative cells, you see a lot of increase of these cells. However, if you look more deeply into the phenotype of these cells, there's a lack of this population of CD56 low, CD16 cell high cells that you see in the IL-15 transgenic mouse. So these mice are going to need the addition of the human IL-15 to get really functionally mature NK cell populations. The other interesting feature of this FLT3 transgenic mouse is that you have increased population of the human immune cells in the small intestine and the large intestine. So the top, there's 2 different NSG mice. This is the small intestine and the large intestine of the NSG, and this is the FLT3 ligand expressing mouse down here in the bottom. And this is just staining for human CD45 and all this brown staining that you see here. But these cell populations include both CD4 and CD8 T cells and some other cell populations. So the summary of this model compared to the NSG, you've got more human T cells, more myeloid cells, more NK cells, but they are a cell population that is in an intermediate stage of development. There's more human conventional and plasmacytoid dendritic cells. Data that I didn't have time to show you is that if you stimulate these immune populations through toll-like receptor 4, 9, and 3, You can activate these cell populations with these molecules. You can get cytokine release. So these are functionally activated, functionally active cells within this immune compartment of these mice. So there's a lot of enhancement of mucosal sites in terms of repopulation of these cells, raising the potential for modeling a number of autoimmune diseases. And again, we can co-engraft these mice with tumors, and we're beginning to start using these mice in very interesting studies. So this is a chart that once you get a copy of these slides, within the next week or so, you get a copy of these slides by attending today. You'll get this chart that helps you kind of summarize everything that I just went through. And really what you can see is what I talked about is that the NSG mice are a good tool if you're looking at T cells in particular. And the way to look at this chart is that if you're in light green, their cells are present, but they're at low frequency. If they're a darker green, there's more of them. For example, in the NK cell populations, if you compare the NSG to the NSG IL-15, you're going to have more of those cells. And then the most will be in the darkest green. But there's something that I should point out that I haven't mentioned yet. All of these strains make B cells. If you look at their peripheral blood, you look at their spleen, you can find CD19 and CD20 positive cells. Those B cells will make IgM. If you put these mice in and you inject them with molecules to induce an immune response with a vaccine or an infectious disease like Epstein-Barr virus or dengue virus or something like that, you will see a small increase in IgG, but the overall ability of B cells to undergo class switching is extremely limited. And this is an active area of research and trying to overcome these B cell responses in these animals. But what I've done here is provided you not only with a summary of the increases in the cell populations across these, I've also summarized here in terms of what these models are primarily being used for. Good T cell model for NSG. For SGM3 includes good T cell, Treg, myeloid, and mast cell work. For the IL-15, really an increased focus on both T cells and in particular the natural killer cell compartment, as you might expect. With the F1 hybrid here, we've got both the best of both worlds by combining these two strains together. So T cells, Tregs, myeloid, and natural killer cells. The jury is still out on mast cells. I suspect that they're also going to be a good mast cell model, but we're analyzing that data, so I don't want to make that conclusion without seeing the results of that data first. And the same is true with the FLT3 ligand. I haven't seen the data on the Tregs yet or the mast cells, so I don't really know the results of that yet, but we'll report that out as soon as we get it. But this is a really good model for T cells, myeloids, and dendritic cells. And so it's a really wonderful model for doing a lot of work and really kind of expanding the overall hematopoietic compartment in these mice. So the hematopoietic platform summary here, really I want you to recognize that JAX creates and distributes mice engrafted with human cord blood-derived CD3 hematopoietic cells. In other words, on a monthly basis, we're taking these first 3 platforms and we're about to start doing this with these 2 platforms. We don't have them on the shelf, yes, but that will happen this year in 2023. We'll start hematopoietically engrafting these mice. We validate their engraftment at 8 and 12 weeks post-engraftment, depending on which model we're talking about. And so you can get genetic engrafted confirmed mice to just roll directly into your studies. These mice develop stable and multi-lineage and immune engraftment. Certain immune populations require human-specific growth factors for their development and function. So the model that the population of interest to you will help drive which platform. And again, this is kind of another overview of these platforms and the cell populations that are going to be most directly associated with these.